Hello, everyone, and welcome. My name is Andrew Young, and today I'm going to talk about Sandia's experiences with ARM to date. So let's get some basics out of the way here first. Why does Sandia want to spend time, or have we chosen to spend time with ARM? Well, for the past decade, it's pretty clear that the x86 market has dominated the HPC ecosystem, particularly with offerings from Intel and AMD. We do have IBM Power options as well. However, while they are fairly high performance, the performance per dollar is often much lower. And any market that we see dominated by a single ecosystem can typically have less innovation and certainly higher costs if we're not careful. So it's important for the DOE and NNSA to have several options when trying to select for current and future HPC systems. This is important so we can tailor to our specific mission needs, help promote effective competition whenever possible, and the NNSA always benefits from broader vendor engagement and ecosystem deployment whenever we choose to do such activities. So in the context of working with ARM, there's several timelines that we've really tried to focus on. There's a short-term option for, making sure that we have more options for selecting for system deployments, both at the CTS, ATS, and prototype system level. From a medium-term perspective, we want to influence and see HPC-specific chip offerings with special customization for the selection of the right amount of cores and memory systems in particular. And potentially there's an opportunity to have a longer term impact on the IP itself that goes into these CPUs. And we really hope to be able to play a role and have an influence in that space as well. So Sandia's had a long history with ARM. We've had embedded ARM devices running around the labs for many years at this point. Not many people know this, but Sandia actually has a fab that has worked with ARM for many years for other national security missions. And in the context of HPC and data centers, we've had test beds and evaluation platforms that have had ARM options dating before my time even at Sandia since 2012. More recently, we've had a strong focus on some of the Marvell, Fujitsu, and NVIDIA offerings. And here you can see a quick sort of snapshot of some, but certainly not all of our testbed systems with ARM CPUs. The most notable one here being what we chose to have as our first Vanguard platform, which is Astra. So I figure at this point, most people have heard about Astra, but very quickly, it was deployed initially in 2018 as a prototype system to evaluate and really prove out the ARM ecosystem for DOE and NNSA needs. Consists of almost 2,600 CPUs based on the Marvell Thunder X2 CPU, but is otherwise a pretty interesting supercomputing system with significant amounts of memory, fast Mellanox, EDR, InfiniBand interconnect, and all-flash Lustre for storage system as well. There's some details in our previous SC paper titled The Chronicles of Astra. So early in our evaluation of ARM platforms, we had significant concerns surrounding the software. Specifically, we're worried about the immaturity of a production compiler and math libraries. Some of our libraries wouldn't even build and certainly weren't optimized for ARM platforms, and there were significant concerns about MPI runtime performance. So as part of this Vanguard Astra activity, Sandia developed something called ATSE, the Advanced TRILAB Software Environment. Now, admittedly, originally the A started for ARM, but it's since expanded because we find this to be far more useful beyond just ARM. And I think that's an important thing that you'll see here. So the idea here was that we were going to utilize TOS and work with our colleagues at Livermore to build a robust operating system, as well as an extensive developer environment, and include specific components from vendors whenever possible. So what does this look like today? Well, as I mentioned, ATSE is a collaboration, not only across the TRILABs, but also with our vendor partners and the wider HPC community. And there's many pieces to this puzzle that we've assembled in ATSE. We have some interesting components, specifically with HPE Cluster Manager that can boot all of Astra. It's 2,600 nodes in just a couple of minutes. We've tested and evaluated HPE's MPI as well as OpenMPI offerings, the ARM compilers, which I'll talk more about in a minute, as well as bringing in many different open source components along the way, built on this TOS or Red Hat equivalent operating system, really to provide this really full programming environment that our code teams could then pick up and utilize effectively and efficiently. So, okay, we talked a little bit about some compilers here and our needs. It should simply suffice to say that our developers expect production class compilers and math libraries. They are critical for our codes today. So we started working with the ARM HPC compiler and performance libraries products, primarily developed out of the UK, and really set forth with a contract to help ensure that this could mature and work effectively for Astra as well as other ARM systems. So we recognized early on that we would need this engagement really for performance correctness, focusing on enabling new features, because at the time, these tools were much less mature than other offerings in the x86 world. And it really was an opportunity to also look at some other things, specifically with some Fortran front end and flying compiler operations. So with that, we've seen many improvements to the ARM compiler in the context of HPC. We've seen much significant improvements with Fortran, thanks to collaborations with our friends at LANL. We've seen improvements into the OpenMP runtime stack, pointed out by some of the benchmarking that we've been able to do. We've seen significant improvements in vectorization, not only for Neon, which we see most heavily utilized in the Thunder X2 type of CPUs, but also SVE as well, as we're certainly interested and invested in that. We've also made improvements to some of our C++ portability layers, most notably Raja and Cocos. Oftentimes we use a TRILAB set of mini apps, but we've also brought in the wider DOE ECP mini app suite when and where possible. And over the past several years, we've seen some fairly extreme speedups for some kernels and benchmarks, and that's really a good sign that the ecosystem for ARM has and will continue to improve substantially. And we've seen that some of our investments, specifically with Vanguard and the contracts therein, have really fed into some product release improvements as well, which we're pretty excited about. So another thing that we've really kind of tried to focus on is containers. We really want to be able to bring in as much as we can to test and evaluate on these ARM test beds and platforms, including Astra itself. However, this container DevOps model that has been so strong in the cloud world and more recently in HPC quickly becomes a problem when our target deployment looks nothing like, say, my laptop or workstation in which I build my container image and then choose to deploy it. So what do we do about this? Well, we've invested heavily and worked with Red Hat on PODMAN and Builda in particular. The idea here is that we can enable an on-premise container build infrastructure on our ARM system, on Astra and Stria, using PODMAN. Maintains user level permissions. This is something we can't really do with Docker. It leverages shadow utility mappers and some clever techniques with overlay and fuse for user-based mounting operations. This workflow where we use PODMAN to build a container image, specifically ATSE in particular in this example. We can then build our application directly on top of ATSE if you want. This integrates well with our GitLab container registry services, and then we can convert that to a Singularity image and run that potentially at full system scale. And that's a really powerful notion for us. We've demonstrated this, and we think this is the first demonstration of this sort of, on-premise, container build infrastructure on an HPC system. We do see a lot of value in PODMAN. It's CLI equivalent to Docker. So if you know how to work with Docker, you can work with PODMAN as well. And we think this is also going to have some spillover impacts with the wider community and some of the hyperscaler deployments in the next couple of years. So as I mentioned, we can use containers to bring in some new software and test and evaluate on our systems very fast and efficiently. However, containers have also been really useful for enabling the ATSE programming environment. As ATSE consists of several different compilers, many different MPI implementations, and a whole slew of different libraries, we really have to pay close attention to how we release ATSE and mark different versions. And containers have been really useful for this. First, in release testing, before we release a new version of ATSE, we build it in a container and we test it, and we can run it at full system scale potentially on our key applications that we care about within Sandia and the NNSA to make sure that our ATSE stack is well and validated. We can also and have used containerized ATSE to roll back. Sometimes we do still find a bug at scale, and we can roll back to a previous version of ATSE to do some interesting debugging at scale. And this is also really useful for cross-system synchronization, where maybe we have similar bits of hardware on different networks with different security profiles, and being able to build our tools and our codes in containers with ATSE and move them across those network planes is something that's proved to be rather important. So one demonstration of this is with SPARC. SPARC is Sandia's next generation high performance CFD and thermal modeling code. We've deployed it extensively on Astra, and we've been able to do so also within a container. Here you can see there's an example where we quickly took an optimization that was suggested from some of our partners and vendors, and made that optimization directly within the container and built SPARC from it. And we're able to see a slight performance improvement using this optimization at significant scale. And being able to quickly test and prototype this in a container has proved to be a very powerful notion for us. For those interested, generally we see near native performance using containers. Essentially, this is uninteresting yet very good news. There is no significant overhead introduced by using, for instance, singularity containers at scale. And this is confirmed with other previous assertions from other work over the years. So the short story is containers are just as performant, and your performance really depends on what you build in your container. So we've also done some work, obviously, with GPUs with ARM. We've originally started working with NVIDIA back in 2019 and 2020, really to see and test out some of the new CUDA-enabled ARM plus NVIDIA GPU offerings. We were able to put some NVIDIA GPUs directly in Thunder X2 hardware and attached to Astra and Stria and start to evaluate that. We've now included the NVIDIA GPU libraries and compilers into the ATSE stack and tested several benchmarks. I think this example here is with HPL, and make sure some of our initial Cocos application tests make good progress. We've seen some bugs initially. However, the latest releases have been much more stable, and most of the components seem to be working well. There's a couple little bugs that we're going to have to work out, but all signs point to this ARM plus GPU offering really becoming mature in this setting, and we're happy to play a part in that. So what about Astra today? Well, Astra is in production use and has been well utilized by many users across the TRILAB community. A lot of our users are finding the scale and turnaround system to be turnaround time within the system to be incredibly appealing. And this is currently running mission workloads to support some of our interesting work in the stockpiled stewardship program at Sandia. It will be a production resource at this point. Originally designed as a prototype system, Astra is now a production resource that will remain so for the rest of its lifetime. And it played a critical role in the most recent NNSA ATDM level 1 milestone. It really allowed us to show the code teams that the system really was viable for their codes in particular. And conversely, it really helped us improve some of our configurations with Cocos and Trilinos, and really make sure that we were ready for our production users. So with that, we've come to the obvious question of, is ARM ready for our NNSA production use cases? And I think my previous slide said everything we need to there. We have the availability of production class compilers that are performant. We've broadened the ecosystem to support multiple different avenues for developers in the context of HPC. And we've seen competitive performance compared to our existing NNSA systems. And there's certainly a strong case for ARM in the performance per dollar perspective. And we've since been working on improving reliability and seen that reliability can now generally meet production class system needs, which is a really important goal. So what's next? Well, obviously, most people have probably heard about the Los Alamos announcement regarding a new partnership between Los Alamos and NVIDIA on a new, yet to be fully detailed system in 2023. We're very excited for this and are really looking forward to further information about this system. This really means that the next generation of ARM processors will be in production use across the NNSA. This continues to extend and build across the ecosystem and ensure that ARM in HPC continues to mature. That being said, this is just a small perspective here, where I think we're going to see a lot more of these types of machines, most notably the ELP system that was announced as well recently from CSCS to be deployed in 2023. This is really exciting news here, and we're looking forward to helping in this enablement. There's a lot more that we could do as well. So ARM is relatively capable as an HPC processor offering and ecosystem. We've demonstrated this with Astra, and we're continuing to move forward with our latest generation of GPU and Fujitsu A64FX testbeds. But the future of ARM, is sort of our longer term goals started to allude, is a little bit unclear at this time. We really want to be able to engage in custom IP and heavily optimized processors. And there's still much more work that we really want to do and investigate with the ARM community in this activity. Most of the ARM IP that we see that's used by Marvell, Ampere, potentially NVIDIA, Amazon, is really developed from standard and commodity offerings at this point. Obviously, the Fujitsu system is an in-house implementation and is rather interesting and unique, but comes at a pretty significant cost, on the order of a full cost of an exascale system, and that takes a significantly more investment that we may be comfortable with. And it's not clear where the diversity of some of these cores are really going to come from in the future. A lot of this really depends on what happens with the NVIDIA and ARM acquisition. And we really want to make sure that we still have alternative options for our CPU selection in the DOE NNSA. But that doesn't necessarily mean that that's going to give us all the advantage we're originally out and searching for. So with that, I think we're really excited to see what happens next in the ARM community, and I hope to play a really critical role moving forward in this. And with that, I think I'll conclude and look forward to the follow-up discussion session. Thank you very much for your time.